Okay, it's already
It's already
3:30. Let's
3:30.
wait
Let's
for
wait for
one more minute. Then
one
we
more
will
minute.
start
Then
the
we will
session.
start the session. Okay, then I will start the session. Uh, Good evening, everyone. My name is Satyam Kalpitavsan, and I'm your currently the TA of this course, that is Smart Grid Basic to Advanced Technologies, whose instructors are Professor M.P. Padisar and Professor Premlata Janana. And this is your fifth tutorial session. And these are the topics which I am going to cover today. That is the basics of microgrid, then islanding detection technique, that is passive, active, and hybrid techniques, and some communication-based technique also. And the last one is the smart grid production. These are the three topics which I am going to cover today. So, starting with the first topic, that is the basic microgrid definition. Then my screen is visible. Anyone please confirm? And its resolution is as per the according to you. Anyone please confirm that my screen is visible and the fonts are visible to you also.
Yes, sir,
Seems to be.
visible.
Anyone please confirm? My screen is visible now.
Yes, sir.
Anyone? By opening mic you can
Yes, sir.
tell me that, or write in the chat box whether my screen is visible perfectly or not.
Yes, sir. Yes, sir, visible.
Anyone
Anyone
seems
seems to.
a
The
screen is
screen is
visible or
visible
not?
already.
Okay, then
Okay,
I
then
hope
I
that
hope
my
that
screen
my
is
screen is
visible to
visible to
you.
you. Okay, let's starting the session. That is the first basic definition of the microgrid. That I have written the two definitions. One related to this U.S. Department of Energy, and second was the SIGRE C6.22 working group, which is also followed by this IEEE standard 2030.7 by defining the microgrid definition. This microgrid, as defined by the U.S. Department of Energy, as a group of interconnected loads and distributed energy resources within clearly defined electrical boundaries that acts as a single controllable entity with respect to grid. A microgrid can connect and disconnect from the grid to enable its operation to both grid connected or islanded mode. It means that you can have the distributed energy generation sources such as this wind, battery storage, and PV based, solar PV based technology, and other also like hydro, small hydro comes in renewables, and some other like ocean wave, this kind of distributed energy sources, and it also connected with this grid. It can be connected with the grid or acts as an islanded condition also. It means that this grid which is the actual grid entity which we give this conventional, and it can be connected to this microgrid using some point of common coupling, with a point of common coupling which can be a circuit breaker or anything, which connects between this our grid and this microgrid generation system. And it's also a within the electrical boundaries. It must not be that it should not be connected, and it is at a far location. And the second definition, that SIGRE C6.22 Working Group Microgrid Evolution Roadmap and the International District Energy Association, that is IDEA, and a company, that is ARUB, that is engineering company, and IEEE standard 2030.7, they all define microgrid in the similar fashion as Department of Energy defines, US Department of Energy defines, with the similar terms as it also have the load, distributed energy sources, which include distributed generation, storage, load, and control. The concept of operating with or without the grid. With or with the grid connected system can be part of this microgrid system, or it can be an islanded system also. Microgrid, separate entity which providing some resources, that energy power to the load which is connected in within that boundary itself. In the right side, I have given one image also where you can see the initial, that is the utility grid with which we have conventionally, and also it is connected to one distribution transformer. Then it connected to this AC microgrid through PCC. PCC is the point of common coupling, and which connect or disconnect this microgrid. So as you can see at this bar, this AC bus bar, there are certain loads are connected, that is tier 1 loads, tier 2 loads, and tier 3 loads based on the energy consumption. And also in the upper side, some renewable sources are also connected, such as the PV system. It is connected to DC to AC converter because it generates DC, then you have to convert into AC to connect this AC bus bar. Then you have a wind turbine also which have AC, DC, AC component for the conversion. As already I have told in the previous tutorial sessions, that it also have a DC converter also, that DC to DC converter inside of also. In case of this DFIG based system, double fed induction generator. And you have a EV charger. EV charger says that if your vehicle is capable of delivering power or not, that is V2G services or not. In that case also you need DC to AC converter. If it is outside of your vehicle, it is an off-board charger. If it is inside of this EV, that is an on-board charger. And you also have this battery backup also during the emergency situations, which is also connected to this DC to AC converter. So you can connect with this AC bus bar this renewable sources using DC to AC converter or AC to DC to AC converter. Okay. So and this is also connected to the utility grid also through this point of common coupling. So after this definition of this microgrid, I have one question for you. There are these 6 statements are there. You have to determine that which statements are true and which is false regarding this microgrid. Basic definition. Please write in the chat box. I am giving you 4 minutes to solve this question. You can write in the chat box, or you can open your mic and tell me the answer. Any answers? Anybody? Last 1 minute. Any answers? Shruti, Shiv, Sai, Radha, Shibna. Anybody? Any answers? Okay. A, B, D, E, F is false. Okay. A, B, D, E, F are false. I have got one answer. Anybody else? Any other answers? Okay, let's jump to the answer part. Uh, let's read the statements first. Coming to the first statement, what it is saying that microgrids operate independently of the main utility grid and do not require any connection to it for power supply. Actually, that is wrong because I have told you that it is connected through this in the right side figure. If you can see that this is your utility grid, and it is connected to right side this microgrid setup through this on and off switch. This common switch is there, but this is a point of common coupling which can be acts as a make microgrid as a islanding situation, acts either in the islanding situation or in grid connected situation also. So it can independently operate. So the first statement is false. Coming to the B part, it says that microgrids are primarily designed for urban areas and cannot effectively survive rural or remote areas. That is false. Why? Because from the name itself, it is showing that this is a microgrid setup. So it can act as a separate energy generating source for a rural location where this utility grid cannot be connected, or the power supply cannot reach at some these places. So for the example, I can say that this if you the example of this Chhattisgarh, in the near rural area, if you see this Bastar area and lower region of this, the Dantewada region, there these mountainous regions are there. And in the mountainous region, there is a lot of places there that there is a no grid connected system you can place because the in mountainous region and the more number of trees are there. To place the wire or to provide this electricity supplies to those villages, you have to connect with this utility grid. So that is not possible. So what is the solution there? You can set up a microgrid there through the solar PV based system. By that you can use inverter for this conversion of DC to AC. Then you can feed this power to these villages. So it can independently operate, and it is mainly for this rural area or remote locations. Coming to C part, that is a microgrid typically relies solely on the renewable energy sources such as solar and wind for their power generation. Actually, that is correct. Correct in what sense? Not that is false. Why? This do not depend upon solely on the renewable energy sources such as solar and wind. It also depends upon this energy storage system also. How much backup is there? Second, there are other generating sources also there, such as hydrogen. Hydrogen is one of this booming topic nowadays, and other are such as ocean based energy generation system. So this is not solely depend upon the solar and wind. So this is also false. Coming to D part, this microgrid are incapable of islanding themselves during emergencies or grid failure without manual intervention. That is false. The false in what sense? It can automatically island in this microgrids, and it is capable of islanding themselves due to this emergencies or the grid failure situations. And coming to the E part, that microgrid have no significant impact on reducing greenhouse gas emissions since they are primarily rely on the localized power generation. That is also false because it connected because this connect this renewable energy sources to form as a grid, this microgrid. Microgrid means there is a lower power generation as compared to the this utility grid. So this can have capable, and it impact this greenhouse emission by reducing this because there is a higher number of penetration of this renewable energy source. Coming to F part, this microgrid are cost prohibitive and not economically viable for widespread adoption in most areas. That is also false. It is cost effective at some of the locations because if you see this suppose let's the example of this Lakshadweep. So Lakshadweep, it is a far away from this mainland India. So what you do at that location, you can set up this PV based solar generation power plants. By that you can generate electricity at that particular position, and the wind you can also install because there the potential of the wind is also there in the onshore and the offshore. So this microgrid setup can be useful at that remote locations. So these are the solution of this problem. Coming to the next part. Next part, I have written the 6 statements that is related to the right side. You can see this is the basically the microgrid parts, microgrid components, and you have to match with the left side with their characteristic. Suppose there is a control system, so which characteristic in the left side matches with this control system? Okay, try this question. I'm giving you few minutes to solve this. Just first read the statement because the microgrid have many components, so you have to be familiar with that components itself. Let's try this question. And I request everyone to take part in this. Any answers? And if you have any doubt in between of this session, you can open your mic and ask me. And also you can write in the chat box if you want. Any answers? Any
Any
answer
answer
you
you
got?
got?
If
If
you
you
got
got
the
the
first
first
two
two
answers,
answers,
you
you
can
can
also
also
write
write
in
in
the
the
chat
chat
box
box
that
that
first
first
one,
one.
first is A or first is B. That kind of solution you can also write. Okay, I got one answer that first of B, third of F, fourth E, fifth A, and sixth of C. Okay, let's revisit the question and see whether these options are matching with the with which option in the right side. So let's read the first step. First statement is saying that the ability of a microgrid to disconnect from the main utility grid and operate autonomously during emergencies of the grid failure. Actually, this is the condition of islanding. Why? I have told you that this main utility grid connected to this microgrid, this is the normal operation, that this utility grid, normal grid, which is connected to this microgrid with this point of common coupling, and this microgrid can act as in islanded mode also, not in grid connected mode. So first is B is matching, first of B, this first option is correct. So coming to the second part, that technique used to manage and optimize the distribution of power within a microgrid to ensure efficient utilization and stability. This statement I will explain you based on one example itself. I have one question related to this, how this efficient utilization of power happens within the microgrid and with the grid connected system also. I have one question. So which statement matches with this? So second, if you see, it matches to energy resilience. If you, it can be one of the kind that it is an energy resilience kind of system, because it is technique to manage and optimize the distribution of power within a microgrid. Let's wait for the second and come to the third. The integration of various small scale power generation sources such as solar panels, wind turbines and energy storage system within a microgrid. That is actually this grid interconnection of the various DERs, and these are the DERs also. So E and F option can also be correct, that for the E, because this is also connected to the grid also with the AC bus bar, or you have this distributed energy resources also integration. So coming to the fourth part, that mechanism for connecting a microgrid with the main utility grid to exchange power and support grid stability. This is mechanism for connecting. So mechanism, how can you connect? This is the using this grid interconnection. So mechanism to connect a microgrid with a main utility, it is grid interconnection. So first answer is B, second answer that is C, third option is E. Coming to this this solar power, third option is F, and fourth is connected to E. Coming to this fifth part, that technologies and algorithm employed to monitor, manage and control the operation. So fifth in itself the control came. So fifth of A is correct. Coming to C part, that the capacity of a microgrid to maintain continuous power supply in the face of disturbance or this enhancer reliability. Actually, the options 6 is connected to this C part. This is the energy resilience, and this technique to manage and optimize this second option, it will be connected to D, because here if you see in the second part, it is manage and optimize. It means that what amount of power to be transferred from microgrid to the load or grid to load. That is actually the load balancing. This I will show you with one example itself in the coming slides. So coming to this modes of operation, this modes of operation of the microgrid, first one is grid connected operation mode. So first mode is when the this microgrid is connected to grid itself. Second mode is when it is not connected to grid. Not connected to grid, it means that it is an islanded condition. And third is such that when it is in islanded operation and it is jumping and going into this grid connected mode, that is the third mode of operation. So first mode of operation is such that it is a grid connected operation. Second is when it is not connected to the main grid, that is an islanded situation. Third is when it is moving from this islanded situation to the grid connected operation, that is the grid connect control. That is the third modes of operation. So coming to this, after this this modes of operation, coming to the most important topic, which is also useful for your solving the assignment yourself, that this islanding topic. For actually, before going this islanding, major portion of this islanded situations, first is what is the basic definition of islanded system. So according to this IEEE standard, it defines this islanded situation as a condition in which a portion of an area electric power systems is energized solely by one or more local EPSs, the energy power generating sources, through the associated PCCs, point of common coupling, while that portion of the area EPS is electrically separated from the rest of area of the EPS. It means that you have area, that is the area, it means the electric power source, which is the main grid, utility grid, which is connected with this other rest of this other EPSs, which is have a self-generating capacity, and it can act this portion of area EPS electrically separated from the rest of area. Means this EPS can be separated from the other EPSs through this point of common coupling. This if you open this, maybe a circuit breaker can be there. If you open the circuit breaker, then this right side EPS, it will be isolated from the rest of the EPSs. So in the image also, in the first image, if you see, this is the utility substation which is connected to this microgrid setup, and it is connected to one CB in between. So if you disconnect it, this whole of this microgrid gets islanded in this situation, that if you see the remote location where the electrical this generation can be there. So this is the one of the definition. So coming to the right side image, if you see this islanding have a multiple types. Suppose this feeders have, suppose this is a initial image. First if you see where my cursor is there, this is the distribution substation which is connected to the main substation. So this distributed substation have bulk power supply generation transfer capacity. Then it is connected to some feeders in such that, suppose in the first tie line, if you see the tie line, the first feeder is connected to this generator. Second is these other feeders are there, second, third, fourth, and in the right side with the last feeder, the one generating source, that is generator, is there. Second, if you come to the second second feeder inside, that is a single customer microgrid. Single customer microgrid means this customer can generate electricity at their utility itself, and you consume itself, and also can transfer this power to the grid also through this feeder substation, through this tie line, and then this feeder substation. And if you see this partial feeder microgrid, this microgrid have this self-generating capacity, and it also connected to grid, and it can also send the power one generating plant to the other generative plant within this partial feeder microgrid itself. So first type of microgrid, that single customer microgrid. Single customer microgrid means it will generate this electricity at their location and utilize it and cancel. And in the partial feeder microgrid, they have the generating capacity and they can exchange the power within itself and also can transfer the power to the grid. Okay. So these are the main types. So this is the this one of the question I have given, that you have to evaluate the followings which are effective. These are the effect occur due to the failure or in the disconnection of the unintended islanding event. It means that when I want this microgrid to be isolated from the main grid, at that particular situation it failed to operate. So what kind of failure effects can come into the detection of this unintentional islanding event? So you have to tell me that which options are correct from this A to G. Please solve this question. That is the only the effect occurred due to the failure in detection of the unintended islanding event. So you have to tell me that which options are correct related to this failure. Okay, I have got this answer that all options are correct. Any other? Anybody else? Please give a try. I request you to give a try to this question. Each statement has its own uh, this explanation. So if you know the background, you can explain it. Anybody else? I have got one answer that all are correct. Okay, I have got one more answer from the Gobi Krishna that A, B, C, E, F is correct. A, B, C means D is only false. Inverter control means switching. Okay. Okay, let me explain this question with a real life practical situation. Uh, Let me take one new slide. Suppose, suppose one hybrid inverter I have. Hybrid I will explain in this course that what is meaning of this hybrid inverter. This hybrid inverter take the supply from the PV itself and supply this connect. It can be connected to this inverter and give this three-phase supply. This three-phase hybrid inverter is there, and it also connected to this battery also for this maintaining this point of common coupling capacitor voltage. This is also connected to this inverter, and this hybrid inverter is also connected with some circuit breaker to the grid also. So when this PV generating more power, suppose this is the load curve, this 6 a.m. it is started, this PV generation starts, and during this 1 to 2 p.m. it go on at a peak level, then at 6 p.m. it stops. So PV generation profile during the 1 to 2 p.m. it will be used. So generation capacity is high. So what if this hybrid inverter will do? Take this power from this hybrid PV and send this power to the grid or to the load. So suppose there is a case that your generation, your microgrid generation is greater than what the load is consuming. So this difference, that microgrid minus P load, you can send this power to this utility grid itself. So suppose the generation is low. Suppose this PV generation is low. So what it will do? It will take from the battery itself and maintain this point of carbon coupling, this capacitor voltage at this location, and then this power, this transfer this power to this load. And if it will not, there will be situation that this battery should not discharge to certain below SOC. Suppose this is 50% level. So if I have set it that it will not go below 50%, so what will be, it will do? And your this load demand is high. So what it will do? It will take this power from the grid and transfer it to the load. So what situations I came? First, when the microgrid generation is greater than this P load. In this situation, this utility grid taking the extra power, that's in the positive, that how much amount? This microgrid, P microgrid minus PL, amount of power sent it to the grid. Second situation is such that when this battery is there and your load demand is greater than this P microgrid. Microgrid means P battery plus PV generation. So what it will do? It will take this P utility grid power will be negative. Why? Because it is taking power. How much power it will take? That is PL minus P microgrid, what it is delivering. So there are multiple situations is such that when it will take. So suppose there is a situation that this grid is isolated. This grid got islanded. So what will happen in this case? This PV generate in the same amount what it is generating as per its curve, this irradiance curve. So what will happen to this microgrid hybrid inverter case? That your load demand is that only, and the PV is generating more, and you don't have any grid to supply the extra amount of power. So what will happen? This battery will consume this some amount of power to charge, and that extra amount which will occur, that will lead to over voltage. That will lead to over voltage situation. So at that particular time, when the generation of your PV is very high and there is no grid to consume, so this is a problem of over voltage. So stability problem will come in this case. And this may be possibility that this over voltage relay will operate and you may disconnect this PV generation. So this may happen. So this is the main problem with this. So this is the question that read the question that following are the effect due to the failure in the detection of unintended islanding event. So you need to detect that when the grid is disconnected from your microgrid. So such at that particular point, so that you can disconnect this PV generation to avoid this over voltage situation. So first situation is that out of phase reclosing. It means that you have a 3 phase and you disconnected 1 phase. So it may be possibility that your phase imbalance can occur. Out of phase, it means that certain amount of power which is coming to this, suppose this is initially P power is consuming from the each phase, and after disconnection you have this extra P have to be supplied from other sources also, because there is a need. And it is also such that if it is generating 3 P power and 1 P got disconnected, so there is a power imbalance. That power has to fit to the grid, or it should be utilized at some other places also. Second is degradation in the power quality, that voltage and frequency instability. That is such that when the power generation, your grid generation is greater than the load. Okay, in this case that frequency will rise, and when the grid generation is lower than the PL, then in this case the frequency dip will occur. This is the one situation, and second situation is also that voltage will rise when this unintended islanding situation occurs, unintentional. So this is the can relate to this degradation in the power quality. Third is the grid protection interference. Interference is such that, so when there is a disconnection, so suppose there are multiple utilities, suppose this is the one load is connected and it is connected to some other bus bar. Suppose this is the relay connected at this location, this one location, and you have to supply from this microgrid to this load, and from here also it is coming to the load. So this is the grid. Suppose you disconnected this whole system, this second part you disconnected. So the whole amount of power will flow from this microgrid to the load. In that case, this protection, which is because it is a normal operation, that power is going from this source to the load, but this relay which is connected to say between this PL and generating sources, it will assume that this current level got higher and the voltage got higher. So over voltage protection relay will operate and it will disconnect. So grid protection interference will occur, that it may not be a faulty situation, but it can be disconnected due to this sudden disconnection of this microgrid with this normal grid. Coming to the D part, that inverter control mode switching. Inverter control mode switching, what I have already explained, that this hybrid inverter case, taking the example of this hybrid inverter, how it is disconnecting or connecting this PV generation. Coming to this E part, so all options are correct, that A, B, C, D. Coming to the E part, then malfunction of this protective devices, that I have already told that suppose this is over voltage relay operate. So this is not a situation of this fault. Only thing is that it is generating more and it is not a faulty situation. But your relay will sense that the over this voltage at a point of common coupling got higher. So it will disconnect at that particular situation. And coming to F part, that equipment damage. Your PV may be such that the inside of the inverter heating may occur. This can lead to this equipment damage. And this G part is threat to personal or the crewman safety. Suppose one person is operating at this microgrid location where the generating source, the point of coupling or certain load point of view. So if that sudden disconnection of the grid occurs, so the more generation will go to that load. Suppose I take one example itself. If you see in the right side, so if you have a generating source and you have this load, and this load is generating from this microgrid also feeding power to this load, and also this utility grid also generating power and sending to this grid. Suppose this microgrid got disconnected, so whole of the power will flow from this, and suppose at this point, this crewman is working. So what it will experience, that now the grid will have to supply the more power to the load. So sudden increase in power can lead to this crewman which is working there, can relate to this threat to this life can be in danger of this person. So these all are these effects due to the failure in the detection of the unintended islanding event. In the right side image, if you see this islanded mode, I have given one example also, this right side image also, that this PV array, if you see in the front side, that upper side, this PV array is connected to PV control and this circuit breaker also. Then one battery is connected through battery control, and then one super capacitor with super capacitor control. So if you see that each devices have their own control, so that it should disconnect it from the main grid, or when the islanding situation occurs, so it can disconnect to avoid any over voltage or frequency problem. This is the main situation. So coming to the next slide, that related to adaptive protection performance based on microgrid modes of operation, you have to tell me that which of these statements are correct, because if you see that this is the manually happening, that when to disconnect, when to connect, to avoid this over voltage situation. So certain relays are such that their relay settings can adopt to this performance, this protection performance. So you have to tell me from this five statement that which of these statements are correct related to this adaptive protection performance based on microgrid modes of operation. Please try this question. If you have any doubt, you can ask me in between. Open your mic and ask me. And you can also write in the chat box. You have 4 minutes to solve this question.
Visual clear. Hello, sir. Am I audible?
Any answer? If you are not able to understand anything, you can write in the chat box and you can ask. These concepts are very important. Last 1 minute. Any answers? Guys? Okay, let me explain you all. See this right side image. In the right side image, you have a certain blue boxes and certain this black colored boxes and the lines. So you have this microgrid, this which is a completely blue box which is there, and the above that you have a dynamic protection adjustment unit, and in the left side you have a monitoring and diagnosis unit. So this whole system is what I am drawing. This whole system is protection and monitoring unit, and which is connected to this microgrid. So why this relay have to adjust, this will I will explain in the further slide. But from the present situation, you should think that this relay had to adjust this relay setting based on this microgrid operation. So this microgrid send this measurement and local information of distributed generation sources, weather condition, to this monitoring and diagnosis unit. And this monitoring and diagnosis unit give the information to the other systems such as energy management system for optimizing the energy, and this operating condition also sent to this protection monitoring unit, that is the dynamic protection adjustment unit. And then dynamic protection adjustment unit send command to this microgrid through some protection setting and disease disconnection signal based upon this. So in this situation there is a closed loop kind of system is there, so that this should not be disconnected as unintentionally, and this relay had this protection have to coordinate based upon this microgrid data. So let's read the first statement. What it is saying that adaptive protection performance based on the microgrid modes of operation relies solely on this predetermined setting and does not require real-time adjustment. But in the right side figure, I told you that it continuously takes the data of this measurement and the local information of the distributed generation sources for real-time adjustment of the settings. So first statement is false. Coming to this second statement, that adaptive protection scheme in the microgrids are unnecessary as traditional protection schemes are effectively handle this operating scenario. That is also false, because we need this advanced digital type of communication system to automatically optimize this relay setting in the real time itself. Coming to the C part, that adaptive protection performance based on microgrid modes of operation primarily focuses on optimizing power flow and energy efficiency within the microgrid. That is true. That is true in the sense of that it optimizes power flow, which is I have written in this information which give this monitoring and diagnostic unit to energy management system. So it optimizes the energy consumption and energy efficiency within the microgrid itself. Coming to this D part, that adaptive protection system in the microgrids are static and cannot accommodate change in system topology or operational requirement. That is false, because you have to do this structural change and topological change for this adoption of this microgrid and microgrid this protection and monitoring unit. So D statement is false. Coming to the E part, that adaptive protection performance based on microgrid modes of operation primarily concerned with the optimizing protection setting for individual component rather than considering overall system behavior. That is also false. False in what sense? It takes the system behavior, because if you see this measurement of the information of the grid and energy management system plus this measurement of local information of this distributed generation systems also. Not only the energy management system, only it also takes this information of this distributed generation sources also. Okay. So this is C is false and the other statements are, C is true and other statements are false. So coming to this this numerical part, this is a very important numerical part for understanding purposes. This how is transfer of the power is happening between the grid and the microgrid. So please solve this three part. In the third question, that is the some explanation part is there. So you can type in the chat box itself this explanation part. Okay, I am giving you 4 minutes to solve this question. First read is, this is very basic question based upon this concept which I have already told you. If you got the first answer, correct answer of this, then you can write in the chat box itself that first answer is this, second answer is this, third explain the part. Anybody who got the first answer? Just use the power balance. You can also open your mic and tell me the answer. Anybody?
Anybody who got the
Anybody
answer?
who got the answer?
At least first part.
At least first part.
And if you have
And if you have
any doubt, you
any
can
doubt,
ask
you
me.
can ask me. Last 1 minute. If you can write the first first question solution. Anybody? Just use the power balance. Power balance. Okay, I have got the one answer. The 1000 watt axis V and F imbalance. That is actually correct. I have got one correct answer. I request everyone to please try. Please try, because the further concept which I have to explain, that is the far more complex as compared to this. So in the first step, you have to need this conceptual background. Okay. So that way I am moving step by step. Okay, let's come to the solution part. If you see, you have a microgrid setup such that microgrid setup, and which is connected to this utility grid. Utility grid. What in the question is saying that this PV generation, that is a microgrid setup generating 5000 watt, and you have one load also connected. One load is also connected at this point of here. This microgrid load is consuming 4000 watt. Okay, it means that when it is in grid connected mode, when this switch is being off, on condition, then this extra amount, that's 1000 watt of power, should go to this grid itself. This 1000 watt will go to grid when it is a grid connected mode. So first answer is the real power balance in the microgrid when it is islanded is 1000 watt. Okay. Coming to the second part, that determine whether there is a deficit or excess of power, because this is excess. Why? Because this microgrid is generating 5000 watt and this load is consuming only 4000 watt, so 1000 will be excess amount which is not being transferred to the grid when it was initially being transferred to the grid when it is a non-islanded situation. Okay. When it is a non-islanded condition, in the third part, what will be this implication? This voltage will rise and frequency will change. Frequency why it will change? Because the generation here greater than the load demand. So frequency will rise. Frequency will rise in this case. Okay. So this is the correct explanation. So there is there only three concepts are there. You have to see that when it is islanded situation, how much power is being transferred to the utility grid, and when it is connected mode. And second situation is such that what will be its implication on this voltage and the frequency. So coming to this next part, this non-detection zone. Non-detection zone is such that because we have studied that this islanded situation, what is the definition, how it is got islanded, and why should not it happen. I have solved. We have solved one question also, and how much power needs to be transferred, and how over voltage, under frequency or over frequency happens. So this IEEE 1547 standard says that this all DERs have to equip with under voltage, over voltage, or under frequency and over frequency relay to avoid this kind of situation. So when the over voltage situation happens, it should disconnect this PV generation system with the grid, with this microgrid, so that this over voltage should be avoided in the inverter itself, the hybrid inverter itself. So first statement is such that the set point of the voltage relay, that OVR, is set to this minus this 1.1 pu to 0.88 pu. It means that the voltage will move from 0.88 per unit to 1.1 per unit. And in between that, the relay field should not operate, and above that relay should operate. So if the voltage is exceeding 1.1 pu, the over voltage relay will operate. If the voltage is lower than this 0.88 pu, then this under voltage relay will operate. This same set of frequency, same with this frequency also. Here the nominal frequency is 60 Hz. So from moving from this, if the under frequency relay is operation, how will operate? If it will detect the frequency lower than 59.3, and this over frequency relay will operate when the frequency is greater than 60.5. So the presence of real and reactive power mismatch lead to this change in voltage and frequency in the islanded microgrid, and the relay failed to detect if the power mismatches are not sufficient to drive this voltage and frequency relay beyond the set point. So this is problem of the relay itself, that suppose this over frequency condition came, but the frequency not move more than 50, this 60.5, then relay will not operate. So it will come into non-detection zone, where it should not operate, but it have to be operated. So hence the NDZ can be defined as the zone of real and reactive power mismatches at which, if islanding occurs, the corresponding relay fail to identify this islanding situation. Okay, in the right side image, if you see, this delta P and delta Q curve is there. So in the over voltage situation, if there is a situation, then it should operate when the voltage exceed this point. So but if the voltage is lower than this, it should not operate. So there may be situation that it is a condition of under voltage or over voltage, but it is detecting as a it is in operating in the non-detection zone, and it is not happening that relay should operate. So if you see in the further slide, what I am giving you, that there are certain standard by which this relay should operate. This there I have given this three statement, that is the IC 61727, IEEE 1547, and VDE ARN 4105. This is related to New Zealand based their grid code based system. So but you can see that is, suppose you focus on this IEEE 1547 relay setting. If you see this, if the voltage is lower than the 50% in this situation, so maximum disconnection time in the second is given that 0.16 second. It means that when the voltage is lower than the 50 to 50%, the relay should operate in 0.16 second itself. This is the maximum disconnection time. It may have to operate after this 0.16 second. So if the voltage is this 50 to 88%, then 2 second of time frame is given. So after that it should operate. In between also it can operate, but the maximum disconnection time is 2 seconds. And also with the over voltage at 88 to 110%, it have to operate. This is a normal operation that I have told you initially itself, that 0.88 to 1.1 pu, it is the normal operation of the relay. This come in the non-detection zone. And 110 to 120% disconnection time is this disconnection time is 1 second, and greater than 120% of this, that is greater than 1.2, it is 0.16 of the disconnection time. So if you see that if you increase the voltage, if your voltage is going above this threshold, then your operating time, that disconnection time, is reducing. So this is a situation to operate that avoid these faulty conditions. So same with these other codes also. That's IEC 61727 and VDAR and 4105. The same settings are also given there also. So from this table, if you see that there is a certain kinds of grid codes are there, so which I have to follow for this when the over voltage or under voltage situations occurs. So this I have given the reference also, that review of distribution generation interconnection standard. You can also see from this paper itself that how other grid codes give this voltage settings and disconnection time. Okay. If you have any doubt, you can write in the chat box also. Okay. And you can ask me by opening your mic. So coming to the next part, that islanding detection techniques, there are multiple techniques are there. That is the active islanding detection technique, passive detection technique, and hybrid islanding detection technique. And last is the communication islanding detection technique. Passive islanding detection technique is such that it continuously monitors the electrical quantities or parameters derived from electrical quantities to identify islanding situation. We will study further of this all types of this islanding situations. And in active islanding detection situation, we inject certain signals, so current or voltage signals, to disrupt the behavior of this inverter. So this also we will study. And the hybrid is combination of this passive and active. And the communication islanding have certain communication channels such as SCADA PLC to monitor this circuit breaker status. So coming to this passive islanding detection technique, its principle is very simple, that comparison of electrical quantities or parameters derived from electrical quantities. Electrical quantities are that voltage, frequency, current, rate of change of frequency, rate of change of phase angle, this d delta by dt. This kind of things have to monitor, and you have to perform some analysis and give the solution that it is an islanding situation or not. Okay. So coming to these techniques, how many types of techniques are there? There are 5 majorly techniques. One is the power quality, impedance, Rokoff. Rokoff is the rate of change of frequency. And fourth is the rate of change of voltage phase angle, that is V angle delta. That delta, rate of change of delta, is the Roko VPA. And last is the signal processing based system. So coming to the first part, that is the power quality based method. Here if you see, in this measurement technique, first this VRMS, that point of common coupling voltage, have been monitored firstly. So there is only one point of connection between this microgrid and this main utility grid, that is the point of common coupling, where it is got, if it is disconnected, then it is a islanding situation. If when it is connected, it is a non-islanding situation. It is a normal operation. So it monitoring this CB voltage, that the voltage circuit breaker which is giving this voltage, or with a monitoring this voltage at the point of common coupling. Then this is converted, this mean of this voltage, that is a 1.1, because if you are taking this data, it will be in the discrete domain, because you cannot get the continuous domain using some processor or something. So whatever you are sensing this voltage, it must have this characteristic that it is in discrete domain. So you should take the mean of this. Then in this method, they have taken this derivative of this VRMS, which is came in through this mean, which is defined as a factor Then they are taking the mean of this again, this A mean of the A, which they are defining as a D. Then they are taking this RMS, that is FRMS of this RMS voltage of this B, with this time duration T minus T to T in the whole duration of this whole time capital T. And then this is defining as the C factor. Then again they are taking the mean of this C, then they are defining this D, and then they have this pre-defined this threshold. If this threshold is greater than or equal to this D, then this is detected as a islander situation. Okay, so there is must be one threshold such that in the passive kind of system that above this threshold it will be declared as a islanded situation, and below that threshold it is a non-islanded situation. If you see in the right side image also, this is a normal voltage curve in the given with at a point of common coupling. Suppose if you see at a 0.4 second, this at a 0.4 second, this islanding situation is occurring. If you see the RMS voltage is fluctuating, but you cannot tell me that this is a situation of this islanding situation. So you take this mean, then you define this factor as a you take the graph, then you will define as the B mean value, then C, then D. Then D is also have certain limit. Suppose this is the D threshold. Then above this D threshold, if it this value goes, then it is a defective as a islander situation. So this is a method of the power quality method. Coming to this impedance monitoring method is such that if you see, this is the grid. This left side where I am, my pointer is there. This is the grid. In the right side, if you see in my pointer, this is the distributed generation sources. And in between this, you have this load in the center. So at the point of common coupling, so if you see that if the normal operation, this whole circuit breaker, this S1 and S2 is connected. So if S1 got disconnected, so when the normal operation of the CB is happening, there is a certain impedance of this load, Z load is there. When you are measuring this voltage and current at the point of common coupling, thus that will give the ratio of the V by E, that is Z load, when this CB is in closed condition. When this grid got disconnected, then this Z load will change. This Z load will change, and the voltage which is depicted as V by I, because the current now which is coming is solely depend upon this distributed generation where it is in islander situation. So you take this Z which is new, which is after islander situation, Z old when it is a grid connected. So if you define this threshold also, take this del Z. If del Z is greater than Z threshold, then it is a condition of islander. If it is a less than or equal to certain threshold, then it is a non-islander situation. That is based on this impedance monitoring method. Okay. So coming to this next part, that is the Rocco-Bess method. This is a rate of change of frequency. In this situation, at the point of common coupling, we measure this frequency of the voltage, frequency of the signal. This suppose initially it is a 60 Hz system. Then we measure the frequency of the signal. Then we measure this rate of change of frequency. How you measure this rate of change of frequency? In the previous sessions also I have told that you should take this del F, del frequency change, or you can take also this frequency is equal to 1 upon 2 pi del phi by del t. In that certain time duration, you should take the phasor difference between the voltage and current and divide it by 2 pi, you get this frequency. And after that, you can check this del df by dt. Okay. And also you have a certain measurement window is also there, after which you should measure this df by dt. Suppose there is a certain zones are also there, above which this df by dt, if df by dt is greater than certain threshold in that operating zone, then it will be declared as this is a islander situation, because if you see when the islander situation is occur, the frequency will go on increasing, because if the generation is greater from this microgrid, and the load is lower at that particular instant. And also you have a certain this detection time there. If you see, this is a 200 millisecond, so below which you can see this power imbalance is there. If the power imbalance is more, then the this detection time is lower, because the rate of change of frequency is very higher at that particular moment. So in the coming, this Rokov based method is also depend upon this loads also. If the power constant power load or constant current and constant impedance loads are there, then the this Rokov will also depend. What is constant power? In that situation, the power is constant, which is equal to Vi. If the or you can say that V square by Z, V square by Z. If you see that if the this voltage will increase, then impedance will reduce, and that impedance will also increase to maintain this constant power. And in the constant current, if you see, power is equal to Vi, current is constant, it means that as the voltage increases, this power will increase. Same with this constant impedance, that power is proportional to V square. The voltage will increase, this power. If you see that if you sum up this situation, that then you can write is like that power is equal to constant, if the constant power is there, certain Kp, plus K, constant current is there, you can proportional to constant I, plus if it is a constant impedance, you can write it as a V squared. Okay, this is basically this situation of this. If you're writing this is known as the JIP model, that is the impedance current power, that is the JIP based load modeling, JIP model. In this situation also, your Rokov will vary. And this figure is also showing that this you have a different power levels, this constant different loads, then this Rokov, this tripping time, and the power imbalance is also changing. Coming to this next part also, based upon this power factor also, between the difference between the tan inverse Q by P, or you can also say that this between this delta phi between the voltage and current also, then this this Rokov will change. And it also depend upon the inertia also. If you see this, if the H is varies, because if you remember this swing equation, that is GH by pi F, d square delta by dt square is equal to Pm minus Pe. So when the power imbalance is there, then this H will vary at that, according to that, to maintain that. So this with this H variation also, this Rokov will vary. And coming to this L also, this L is such that this line impedance also, it will vary. Sorry, this length also, length of the feeder, it also varies with the length of feeder, that is Rokov. So Rokov varies on the various type of parameter, and also with this X by ratio of this line. So main crux is that the drawback of this Rokov method is that it requires a minimum power mismatch of 15%. That is 0.15 times of power imbalance must be there to detect any condition. If you see from this figure also, if you see this, after 0.5 second, it try to this figure out that how this Rokov is changing. This Rokov based method is determining whether this is an islanding situation or not. Coming to the next part, that is the rate of change of phase angle. If you see this rock pad, this is basically this delta change is delta V minus delta I. I is the initial, V is the final value of that. If it is a greater than certain threshold, then it is a islanding situation. If it is a less than certain value, and then it is a non-islanding situation, which is a similar equation as that of this Rokov also. Okay. So coming to this active islanding based, if you have any doubt, you can ask me in between. No issue in that. Okay. We have certain questions also after this, and also have a certain more concept based on this protection system. Okay. Coming to this active islanding based technique, signal injection based technique, this is the first technique. If you see that this is the DC voltage is there, it can be a PV based source, battery based source, and connected to one capacitor, that is a point of common capacitor, common coupling, that is a VDC. It is connected to the inverter, and then it is connected to this circuit breaker CB2, and then point of common coupling, then CB1, and then to transformer, then to grid. Okay, and in between that, at the point of common coupling, you have a RLC load. So what I am saying that in the normal operation, this load will consume this 50 hertz power, 50 hertz signal, because the voltage and current is in 50 hertz base system. So at that same 50 hertz is also being transferred to the grid or taken from the grid. So in the normal operation, how it is at a 50 hertz. What I am saying that I intentionally inject one kind of disturbance in between of this signal, what is going into in the grid itself. Because if you see the RLC load, it is very high, and with respect to this grid, so grid have a lower impedance, so it will go from this inverter based system to the grid, not in the load. So when it is an off condition, this extra disturbance signal will move to the load when the islanding situation will occur. So what I am saying that you have a ABC frame, I am converting into it into DQ frame, and I am injecting this extra amount, this external frequency which is lower than 50 Hz. Suppose it is I am taking 220 Hz signal, and I am injecting in the D value. If you see in the D also, this same as this I disturbance plus ID reference. So VD comes out to be V omega naught, V omega 1 sin omega dt, which is a normal D reference with the phi 1, and V omega 2 with this other signal. So after conversion from DQ to again ABC frame, you will get this signal, that is V omega naught sin omega naught t. Omega naught is same 50 Hz signal, and you will get omega 1, which is 50 Hz plus 20 Hz, because we are injecting 20 Hz signal, that is 70 Hz signal, and omega 2 is such that that is a 50 Hz minus 20 Hz signal, that is 30 Hz. So variation of frequency, how it is occurring? From 30 to 70 Hz, and in between 50 Hz is also there. And the phase differences also comes out to be this phi, tan inverse omega 1c minus omega l, and the voltage magnitude is also different. So in the right side figure, if you see, I am removing this what I am written for your clarity purpose. So if you see the right side image, at this 1 second, the islanding situation is being created. So before that, this normal operation is there, voltage is maintained at a constant level. So if we are varying this current injection magnitude, that basically the V omega naught and V omega 1, by maintaining the frequency at a constant level. So if you see this voltage got increasing, that is the same value when the islanding situation occurs. This magnitude will increase based upon the how much magnitude of disturbance you are injecting into the system. In the second figure, if you see, I am creating this voltage as a constant, that's V omega 1 is equal to V omega 2, but what I am saying that this frequency omega 1 and omega 2 is being changed from this injected signal, that is the omega disturbance D is being changed. Initially it was 1 Hz, then 10 Hz, 20 Hz, 30 Hz. If you see that there is a change in between this signal based upon the frequency and before and after islanding situation. By observing this figure, you can say that this is an islanding situation based upon this current injection method. If you have any doubt, you can ask me in between. Coming to this comparison, that there are two types of active injection method is there. There is signal active islanding detection technique. That the first one is a signal injection. Second is the positive feedback based technique. So in the first, what I have told you that you should inject one disturbance signal at a frequency which is lower than the normal nominal frequency, that is 50 Hz. and after that you can, based upon this frequency variation, you can tell that this is a islanding situation. Same with this positive feedback based signal. Here the electrical quantities such as frequency, phase angle, voltage deviation are given as a feedback to the inverter. So this is given as a feedback to the inverter. So inverter should adjust based upon this voltage disturbance and make this voltages, this which is coming in the islanding situation, at a constant level. So feedback is designed in such a way that this distributed energy sources operate in this unstable situation. So what are the advantages of this? This distributed energy for the current injection method, it have a negligible NDZ, because what we have learned that non-detection zone is a major problem with this passive based islanding detection technique. So this problem is avoided in this active islanding situations techniques. So, but the drawback here is the power quality degrades. Why? Because you are injecting a disturbance into the system. So the frequency intensely being changed from 30 Hertz to 70 or 80 Hertz. That is the F0, F1 plus F0, FD. What is the FD plus F0 and F0 minus FD? That is three frequencies are coming into the system. And coming to this positive feedback, it also have the negligible non-detection zone, but DR is driven into the unstable mode because we are making intentionally to operate this inverter in the unstable zone. That also leads to this some power quality issues because it is already there in the unstable situation. Coming to this next technique, that is a hybrid islanding detection technique, I am giving one example, that is the voltage imbalance plus frequency set point. See this right side image. Right side image is such that what is this flowchart is saying that you should starting you should measure this, monitor this voltage unbalance. Voltage unbalance factor is defined as V2 by V1. V2 means this is a V2 is 0 sequence, 1 is there, positive sequence 1, negative sequence. So this is the ratio of negative sequence voltage divided by this positive sequence voltage. Then check that this voltage unbalance factor is in acceptable limit or not. If it is in acceptable limit, then you should check this frequency, change the frequency from in the DG itself, from 60 to 59. What I already have told you in the feedback based active detection technique, that inverter take this signal and make the intentionally this inverter to operate in the unstable situation. So if the nominal frequency is 60 Hz, so it creates a unbalanced situation, and check this, monitor the frequency continuously. And if this DG frequency is below 59.2, in that situation which is being created intentionally, then it will send a trip signal to circuit breaker at PCC to restore the frequency set back to 60 Hz. And if it is not, then check the frequency again, that 60 Hz, and after the VU spike. And after if it is checked as the DG frequency is below 59.2 Hz, it is a situation of this islanding. So here you have combined the voltage and the frequency detection both. So voltage plus frequency due to the this feedback based system, making the inverter to operate in the unstable situation. Okay, so this is the hybrid islanding based situation which combine the both this operation, this passive and active. So if you see this last type of islanding detection technique, that is based on this communication rate. First is the PLCC, second is SPD, that is signal produced by disconnect, SCADA, and synchrophasor measurement unit, that is basically what I have already told in previous unit, that PMU based system. So in the first figure, if you see, this is the PCC. PCC is the point of common coupling, and at the right side you have this relay connected. So here this PCC, this circuit breaker point of view, it will measure this PCC voltage, frequency or current and detect any imbalance is taken. Then through some communication channel, it transferred this information to this circuit breaker, and make this circuit breaker to operate, to disconnect or connect based upon the situation of islanded situation or the voltage current frequency of this PCC voltage, point of common coupling voltage. This is the PLCC, and it uses the same communication, the same power line for the communication. And in the second figure I have given you, this is the, suppose this is the bus bar 1, and in the right side if you have this DG at particular point. So I measured the PMU voltage at this bus bar 1, that's V1 angle phi 1, and at that generator point also that's V2 angle phi 2. So in the normal operation this will be in the nominal voltage what I desire. So if there is a islanded situation is there, then this phase angle or voltage magnitude will change. So this GPS through the synchronous phasor system, this analysis has been done to check whether this voltage difference has came or not, or phase angle difference has came or not. So based on that, some decision have been taken that it is a islanding situation or not. Okay. So this is the based on this communication based islanding detection technique. So summarizing this all detection technique, if you see the first part, that is the passive islanding situation, that is Rokov, Rok OVA, and under voltage relay, over voltage relay, under frequency, over voltage frequency. There is a larger NDZ problem is there in the passive based detection technique, which is avoided based upon the signal processing based technique, but the processing power of the signal is higher in this signal based system. And you can also use deep learning based solution or a machine learning based system such as ANN, SVM, that is a support vector machine, and ANN fuzzy logic for detection of this islanding situation. And it also have this lower NDZ compared to this conventional, and also the PQ issues is all there. But the difficulty is very high, because how to implement this deep learning based solution for the real time systems. So this is the end of this microgrid, this islanding detection technique. So we are moving towards this smart grid protection system. So if you have any doubt in between regarding this all other islanding situations, microgrid and islanding detection technique, you can ask me related to that. You can open your mic or you can write in the chat box before I move to this smart grid protection system. Any doubt? You can open your mic and ask me. So I'm assuming that you are not having problem, and if you have problem, we will discuss in after completion of this. So before moving to this main points of this smart grid production, let's go to some basics part. Basic part is such that the operation of the relay and the circuit breaker. How this relay and the circuit breaker operate, that is a very important, because if you have a digital relay or the digital circuit breaker whose relay settings are being changed, so you must have to know this what is the kind of relay setting is there in the conventional also. So if you see this is the bus bar which I am drawing. This is the bus bar I am highlighting. This is the bus bar which is connected to one circuit breaker. This is the circuit view circuit breaker which is connected to this CT. This is connected to CT and it is transferred to the circuit, okay, which is being protected. So if there is a fault in the between, suppose in the normal operation what will be there, this is the I normal which flows, and CT have certain ratio. Suppose it have a n:1 ratio, it will drop down, make this IN2 flow IN by N in this CT itself, CT secondary. Then CT secondary, this relay coil is connected to relay contact. When this relay contact is being closed, then this battery and this coil and this relay contact make the circuit to complete. At that particular time, the one current will flow. This current will flow, this magnetizing current. This magnetic field will here increase in this circuit, and it will make this circuit breaker contact to pull off from this normal connection. This is how this relay operates. Relay is the whole of this system, and how this make this circuit breaker to open. This is the one of the situation that when you have a fault, the current will increase. Current will be greater than this fault current will be greater than I nominal. This fault current will be transferred to this CT secondary. CT secondary. Then this CT secondary will make the relay contact to close. Relay contact will close, and the coil which is connected into this circuit will gets magnetized, and which magnet by magnetization it will make the circuit breaker to open during this fault condition. This is the main basic principle of the operation of the relay and the circuit breaker. So coming to the next topic, first one is the plug setting and second one is the time setting. Plug setting is such that it refers to a current level at which the relay will trip. So you have to define the current level also above which you are considering it as a fault. So because IF is greater than I nominal, is it considered as a fault? IF greater than equal to nominal, it is not a fault. It is a normal operating condition. Okay. So it's expressed as a multiple of the rated current of the protected equipment. For example, a relay with a plug setting of 0.5. If I am setting this plug setting to 0.5, it means that it will operate when 0.5 multiplied by 100 current will flow. It means that 50 amps of current. So current greater than 50 hertz, I will consider it as a fault if the relay setting is at a 0.5. Second thing is that time setting. Time setting, after how much delay it will operate. The relay should trip. This refers to the time delay before the relay trip once the current exceeds the plug setting. The time setting are typically given in terms of the definite time, that in the seconds, or the inverse time, that is the inverse of second per unit current. So based on that characterization, many characterization is there. Suppose the inverse definite mean time, this and suppose this very inverse type of this ADMT relays are there. There are different types of relay are based upon this inverse time settings. This is the inverse time is the time of operation will inversely proportional to current. As current increases, the time of operation will reduce. So this plug setting multiplier is the ratio of this fault current and divided by this pickup current. Pickup current is such that how much pickup current in the previous is that 0.5 multiplied by 100, that is the 50, and the fault current is that greater than the 50 hertz, this you should trip. That is same as the fault current divided by rated CT secondary and the current setting. That is same what I have told, because the rated secondary current is such that I fault divided by 1 by N, which is transferred to the CT secondary, multiplied by the current setting. Current setting is 0.5, which I have taken, and this is a fault current ratio. So before moving to the further slide, I have one question related to this. So in this question, you have to tell me that what is the PSM setting I have to make to operate this based upon this fault current, this 200 amps. You have to solve me this question. So please solve this question. And if you have any doubt, you can open your mic and ask me. You have to tell me that what is the PSM plug setting multiplier. If you want formula, I can also give you. Let me give you formula also. This is the formula you can use for calculating this PSM. We have 2 minutes to solve this question. Anybody? Use this formula which I have given in the slide. Anybody? Shubna, Ashok, Habib, Ritika. Anybody? Can solve? Okay, let's see. I'm explaining this question. Let's make I make you understood this question. Suppose what is given is that here it is given that the fault current is 200 amps and the relay setting is such that 0.5 and the CT ratio is given as 400 is to 5. So this is the relay setting. What I have told, the circuit breaker will operate by the command of relay and the relay will operate based upon the relay setting what is given. So for the relay setting to take this account, what kind of this plug setting, multiplier settings of this relay is there, you have to take the CT secondary current because the CT primary current is being transferred to the CT secondary for the operation to make this circuit breaker on and off. So CT secondary current, what will be CT secondary current? 200 multiplied by 5 by 400. It will come out to be 2.5. Okay. So what is relay setting? Relay setting is given as 0.5. Relay setting is given as 0.5. And what will be this current above which it should operate? What I have already told in the plug setting of this plug setting multiplied by this rated current will give the nominal current above which it should operate. So 5, which is the CT secondary, multiplied by 0.5 is come out to be 2.5 because the 5 current will be the rated, no, because 400 is to 5 is the ratio of this CT ratio is 400 is to 5. So 5 is the nominal current in the secondary. So CT setting will be 5 multiplied by 0.5 is equal to 2.5. So 2.5 is the current above which it should operate in the terms of the secondary. And the relay setting is also 50%. So what will the plug setting multiplier? Is the fault current in the relay coil. What is that? That is a 5 multiplied by 5 by 400 multiplied by 200, which came out to be 2.5. Okay? It is 2.5 divided by the rated pickup current. Pickup current is 5 multiplied by 0.5, that is 2.5.
It is same. So plug setting multiplier will be 1. Okay. So plug setting multiplier will be 1 based upon this fault current. Any doubt in question?
Ashok, 80 will not be the answer. Plug setting multiplier is nearly equal to 1 or less than 1. Okay, have you got this concept? What I am saying that the fault current through this image, suppose this, I remove this for clarity purpose. This current is flowing to this normal line. This current is being transferred to this secondary based upon this term. That is the I fault divided by 1 by N will flow through this secondary. And this will make this relay coil to magnetize, which will pull this relay contact. So there will be some setting that how much time this relay contact to trip, to come in contact, to make this circuit complete. So that is the PSM. PSM is fault current divided by the pickup current. The fault current referred to secondary. So what will be secondary? IF divided by 1 by N divided by pickup. Pickup is relay setting multiplied by secondary current, secondary rated current of this CT. Okay, this is the formula. This is the second question. You please try. I am explaining this. This is the 1, 2, 3, 4, 5, 6, 7 numbers are given. This is the circuit breaker, and which is connected to some transmission line in between. And the bus is given A, B, C. So at a particular situation, this fourth number of circuit breaker got stuck. It is not operating when the fault came. So you have to tell me that the sequence of the circuit breaker which should operate at that particular time. It means that suppose fifth will operate first, then seventh will operate, then second will operate, like that you have to give. Okay, Dhani is saying that please repeat the solution. Okay, let me repeat the question again. Let me remove this. Okay. Okay. See on my cursor how I am saying that. Suppose this 200 amps of current is going in the normal line, and I have connected one CT which take this current and reduce to based upon this turn ratio, and it will give some magnetize one coil based upon this current, and this magnetization coil is connected to one contact, that is the relay contact, and this relay contact when it pull down, it will make this circuit to complete this battery system, and this another coil is there will trip this circuit breaker which is connected to this normal line. So 200 amps of fault current is going. So what the CT will do? CT will do 200 multiplied by 1 by N, that turn ratio. In the question it is given as 5 by 400. So the CT secondary, what current will come in CT secondary? It will come 2.5. So this is the current when the fault came. So what the relay setting has been done to operate make this happen, this relay this circuit breaker to open. So relay setting is set at 0.5. 0.5 of what? What pickup current will be there? Pickup current is such that relay setting multiplied by rated CT secondary current. Rated CT secondary current. What is the relay setting? It is 0.5. Rated secondary turn is 5. Because this is 400 current, 400 amps, and this is a 5 amps of current will flow in the 5 turns. It is pickup current at 2.5. So what will the PSM? PSM will be this 2.5 which is transferred to the secondary, and initial setting what has been done is already at 2.5. So PSM will be 1. This is the basic concept. So I hope that I have explained this concept with Dharni. Please solve this 7th question. Have you got the solution, or Dharni, I have explained your concept? Okay, thank you so much. Please solve this seventh question. You have to tell me that sequence of operation of this circuit breaker. We should operate first, we should operate second, third, fourth, like that. When the fourth circuit breaker got stuck. You have 2 minutes to solve this question. If you have any doubt, you can open your mic and ask me in the chat box also. Okay, one question is there. PSM denotes any indication like if PSM is more means. Okay, let me explain you. Suppose this is a relay contact. Relay contact is such that this is a spherical kind of system, and this is a contact. So when this contact, this I'm circling that this point A will meet this point of contact B, then relay will operate. So if it means that if the relay setting is 0.5, 0.5 means 0.25, it means that this point A will meet the point B, then the contact will be stabilized and relay will operate. Suppose I am at a point A, point A1. So I have to make certain settings that when this A1 should go to the B place. So what I am saying that make this setting as 0.5, this PSM as plug setting multiplier as 0.5. It means that it will move this 0.25 then 0.25 to make this contact. Suppose I am at this position. Okay, this is a 0.75 position. It means that I have to move from here. This is basically the time delay that 0.75 I have done. So you have to make this travel this to make the contact at B. Suppose I have made this PSM at this position only. Sorry. And sorry. So this PSM is at a one position. So it have to follow this whole circle to move at the position B. At that point, the relay setting, their contact has been stabilized. So this is a 0.25, 0.25, 0.25, 0.25. It means that this whole circle you have to follow, and the time delay is more in case of when the PSM is very high. PSM is equal to 1, it means that the time taken to CB to operate is more. When the PSM is equal to 0.5, it takes less time to operate, the CB time is decreases. If the PSM is 0.25, it means that it takes further less time to operate. That is the same concept, that how much time it will take to operate. Because I have told you that two types of setting, that is a plug setting and time setting. Plug setting how you will do? Through relay setting. And how you do the time setting? Using this PSM, the plug setting multiplier. Have you got this concept? Okay. Okay. I think anybody have you solved this seventh problem? Because we are moving slow as compared to the I have slide.
Anybody? Okay, let me explain this question. Uh, this question is saying that consider the protection system as shown in the figure below. The circuit breaker number from the 1 to 7 are of identical type. A single line to ground fault, the LG fault occurs at the point where this arrow has been shown, and at a zero fault impedance. It means that when the fault occurs, the infinite number of current will flow at that particular situation. So you have to operate the all circuit breaker at that point. And at fault F, that this is the point where the fault occurs, but the circuit breaker 4 will stuck and it not operate. So if the relays are coordinated correctly, a valid sequence of circuit breaker operation is. So IF, what is the fault? V by Z. So at when the fault comes at this F point, this fault, this Z impedance, because it is connected to ground itself, the ground impedance which is very high, which is very low. It is zero fault impedance. So fault current will go very high. So you need to disconnect the bus bars quickly. In what it is saying that it is a coordinated relay system. So the relay will coordinate based upon the position at which the fault is located. So the fault, suppose it is at a point F. So which circuit breaker has a nearer position? 4, 5, 6 and 7. So this 4 have to operate at a same point of time because it is connected at a same point of distance. Sorry, so 7 is a longer distance if you see from the length itself. So 5, 6 and 4 should operate. So 4, but 4 got stuck. So which should operate? 5 should operate equally as compared to 6. So 5 and 6 will operate first. Then if you see, then 7 at a this nearer distance to the fault. So then 7 will operate. Then if you see, this 4 is not operating. So 3, the circuit breaker 3 is at a nearer location. So then 3 will operate. Then if you see, then 2 and 1 at a, this 1 at a this nearer position as compared to 2. So then 1 will operate, then 2 will operate. So how will it operate? This time of setting of this 5 is equal to 6. So it will operate less amount of time than 7. Then 3 will operate. Then time taken to 1 to operate will be higher. Then at last time this 2 will operate. So this is basically the time setting of this circuit breaker because this is the zone of this fault. So this is the protection zone of this fault. So this relays this 4, 5, 6, 7 to operate, should operate in this zone. And this 1, 2, 3 may be this secondary kind of protection system. So when this 4, 5, 6, 7 will fail, then 1, 2, 3 will operate. So the time already got this 1:30, 5:30. So I'm stopping at this position, and we have also this slide that related to protection issues in the smart grid. And after in the next coming session we will discuss this. And before moving to that, I have to tell you one concept. Okay, then let make you understand with this protection issue. After that, we will stop this class. That there are various protection issues related to this smart grid. First one is the dynamics in the level of the fault current, because if you know that when the fault occurs, the current level got increased. So this is the dynamics related to that. And this when to operate, which microgrid should be on at that particular time, and that so we will make you understand in the further this tutorial session. So I'm not going there because it will take a lot of time. PPT is from week 1. Okay. Okay. So I'm saying you that you can go to this Swayam portal where you will find this PPTs and video lecture itself. So please see my slide what I am saying that. Suppose you will go to this Swayam portal. This is your Swayam portal when you, after the login Swayam portal. This is after login. If you see this, there this video come. This is the video what you see, and in the down portion you would see this PDF, and in the left portion you see this assignments. This week 1, week 2, week 3, like that. There's assignments are there. In the lower portion you see this tutorial sessions. If you open that link, you will move to one other page where the link of the all PPTs are there. All PPTs and YouTube lectures are there. Of what I take these lectures, I upload on the YouTube channel. The all links are there on that tutorial session link itself. So you should go to this Swayam portal, and the left side and the down portion you will find this tutorial session, this PDF and YouTube link. Okay, have you got, Ritika? Okay. Okay, fine. If you have any doubt, you can ask me. Otherwise, I will stop this session. If you have any doubt, you can ask me. Open your mic and ask me. Uh, we will study this protection related issues and how to mitigate it in the further tutorial session in the coming week. Okay, guys. So thank you very much. I'm stopping the session.